Hi everyone, welcome to this video. I'll be taking you through a project that I have just finished about CNN. This project is in driven data. It's a platform for data scientists where you can find data and practice your data science skills. I participated in this competition called Conservation Practice Area Image Classification. And quickly, let us see what is required of us. Go to problem description. And in this project, we are supposed to come up with a model that can predict images of birds, civets, duckers, hogs, leopards, and other monkeys and rodents. And we are going to help these people in Thai National Park. They did put traps, camera traps, for them to be able to conserve the wild animals. So we have test features here. We have trained features in form of images, and we have trained feature CSV file, and our data set in trained features consist of ID, file path, and site. So site is which the image was taken. Then we have feature data. These are the image. Trained CSV. We have ID, file path, and site. Image there. Then we have trained features like that. Then we are provided with the test features. And these are some of the examples of images that were captured. We are going to train our model for it to identify any of these animals. Some photos, they don't have animals. They are labeled as blank. And these are the boss. We have the antelope, bird, have the civet, hog, leopard, monkey, and rodent. And I'm aware we have a blank column where there is no any animal. And then we are supposed to do our submission in this format. So let me take you quickly on my project and see what we're supposed to do or how I did tackle it. I have done it in two ways. The first way, I built a base model, and then the other way I built transfer. I made use of transfer learning. So I open my Google Colab, and then we go through the project. I have opened my Colab. I import TensorFlow STF, then import TensorFlow Hub, and then see the version that I'm using, and see whether I have GPU available. And these are the results. This is the TF version that I'm using. We have 2.18, and this is the TF Hub version that I'm using. No, I had not yet connected to GPU. Then I import libraries or the tools that I need. I need pandas, need NumPy, matplotlib, and I need Seaborn. First thing I did was to unzip my images, and I did unzip them using this code, unzip content. My images were located here. I downloaded the data from the site and then uploaded it to my Google Drive, and then mounted my Google Drive to my Colab, and then this is the file path to my images. I unzipped them, and there were so many. After I unzipped them, I commented this code just to save space. Then from there is to read the CSV file from Google Drive into Panda data from certain features, and is the file to my CSV. Then I view the first rows of the data frame. So this ID, file path, and site. is the train feature CSV. Then I also did the same to train labels. So in the train labels, we have the ID, and these are the classes of the animals that we have, the answer of the bird. Then we have a column here that is blank. We don't have any animal. Then we have civet, hog, leopard, monkey, and rodent. So these are the train labels. Then from there, then I want to verify the image files. I import OS module from Python, and this the image directory is in content, train features. This is where my images are, and then I want to see how many images that I have. So the image count, I use this code, and I found that I had 16,488 train images. Then I need to view the class distribution. So the class count, I take my train labels and drop the columns ID. I don't need it. And then I print the classes of the accounts. And this is the classes. And these are the counts. So like you can see antelope here, we have 22474 images of antelope. For the bird is 1641. And the rest you can see. Then the D type is 64, float 64. Then I need to view samples of images randomly. I import matplotlib used for displaying images, CV2 used for reading and processing images, random used for select image, used to randomly select the images. Then I have this code here. This one lists all the files in the specified directory. That is the image directory. And then they have to show the 6 random images. You have fig X. This code creates the 2 rows. You can see here, these are the 2 rows and 3 columns. Grid for subplots to display the 6 images. And then the fig, this one, this is the height. The 10 is the height. No, this is the width. The width is the width. And 7 is the height. We have this one, this code. We have this one for args in access.raven. This one flattens the 2-day array of subplots into 1D list so that we can iterate easily. So every time I click this code or I run this code, we are going to say images, different images selected in a randomly manner. Then from there, I need to view the class distribution. I have the PLT figure. So this is the width, this is the height. Then the class counts.plot. I want the kind to be bar. Then the color to be sky blue, the edges to be black. And then we have the label in the X label, that is class distribution. Then the Y label, the number of images. And the title is the class distribution, the data set. And then we have the rotation here 45, and then we can see our graph. So these are the distribution, and from the graph we can see the hog here has the least number of images, and antelope are many. The civet monkey seems to be almost having the same number of images. Then from there, we go to the next. I want to merge my train labels and my train features so that it can be one data frame. And the first thing I do is to define my class names. Our class name, that is the train labels.column. And then I exclude the training at the ID. I don't need it. Then we have this code here. This code finds the column class names with the highest value for each row. Let me show you. It goes through, if you go back here, this one, it will go through all these rows, and it's going to take the highest number, the highest value for each row. So like this one it's going to take 1, and 1 is bird, and then it's going to come up with another column here entitled label, and instead of having all these ones, it's going to remove this one and take bird here. So it's going to get rid of all these one hot and cold and values and make them into categorical values. So what do I mean? Like the way I have said, is going like to go through this row, take the highest value here is 1, and then here we have a column of label, and it's going to label it as bird. So that's what this code does here. And then we'll go all the way, and then it's going to match the train features and the train labels together, and now you can see we have one data frame of all the train and the F that has the train labels and train features matched together. Like we can see, we have the ID, the file path here, the site, and the label. So the first row here, it has got the bird. The second one here is monkey, and for the rest, respect free. Then we get the summary of the train DF. We can see the ID, the file, the site, and the type. So here we have 4 columns, and the data type here is object. So, and this is the memory, so we are good to go. So this code here generate full file paths of images in the dataset by defining the base directory, then takes the ID column which contains the image file name without extension, concatenates the ID and JPG to form image file name, then uses the OS file joined the base directory file name to create the full file path, and then it stores the new column into file path, as we can see here. And then we can view the few file paths to ensure they are correct. So this is the ID, the file path, and then we have it has mixed it with or concatenated it with the JPEG. Then we try to see whether we have the missing files, and in this case we don't have any missing files. The next thing we are going to do is to prepare our data for it to be fitted in our model, and we need image data generator. This one augment, normalize, and pre-process image before feeding them into the model, and we need to perform a few things. We have this code here, data gen. So we rescale. Rescaling ensures that we make our image, make sure that all our images are scaled or having values between 0s and 1 for our model to learn it well. Then rotate 20%, width shift of 20%, height shift 20%, shear or distortion 20%, zoom range, we zoom in and out. Then have horizontal flip, we make it true. Then validation split of 20%. Then we create the training data data. So we have train generator. This one loads images from file paths stored in the PEDAS data frame, that is our train DF. We have our X column here, that is our file path, and then we have our Y column here, that is our label. Then the target size is to form, that is our resized images. Then the batch size of 32 to make sure that at any time our model processes 32 images. Then class mode is categorical, since we have multi-class classification. Then this is a subset of training and shuffle. We make it true to prevent learning order-based biases, so that our model does not learn from any order. That's why we shuffle our data. We do the same for validation data, the same way, but here we don't shuffle to make sure our data is consistent. Then after that, we found that in 191 validated image file names belonging to 8 classes, and then we have that 297 validated images files belonging to 8 class. The next process is for us to define the model, make the model, and then compile the model. So this is just a small and simple model having I think 8 layers. Let's see, 1 2 3 4 5 6 7 8. It just has 8 layers, and I have made a video explaining layers of CNN, what each and every layer does, so you can go check the video. And the first, we have the sequential layer here. This one creates a linear stack of layers. For the CNN, it does not perform any kind of work. It's just the input layer where we put the inputs. Then the second one, and we have convolutional 2D. This one has 2 filters, each size 3 by 3, and we have activation relu just to activate the process. And this one, the work of it is to detect edges and textures and shapes, not going deep into the image. Then we have the max pooling. This one down shapes features, maps them into 1D vector. It reduces feature map size by half of 2 by 2, pooling keeping only the most important features. Then we have this one, the convolutional 2D. This one has 64 filters, size that 3 by 3. Activation is rare. This one, it goes deeper to extract the feature from the images. Then we have max pooling again here. This one it prevents overfitting. Then we have flattened layer here. This one converts the 2D feature maps into 1D vector for fully connected layer. And we have the dense layer of 128 neurons to learn complex patterns, then is helped by rule activation to speed up the learning. And then we have dropouts of 50% here to drop out the neurons to prevent overfitting. And then we have the dense layer or output layer. This one, these 8 neurons here present our 8 classes, and we have the activation softmax. This one, it converts output in probability score sum of 1. Then we compile the model. You can see the 8 layers here. We have total params 23,908,424, and we have the trainable params 23. The same here. We don't have non-trainable params here, so it's as that. Then the last thing we do is to history. We have now this model. We feed it to our train generator and validation data that is in validation generator. There is data here. This one, we feed this data. You see this data and this one to our model. Then we have 10 epochs. We have 10 epochs, and then we have verbose of 1. Verbose means we can see live as the model is being trained. Then from there we can visualize this one. So this is the code. Train loss is equals history loss. That's why we did put history here, so that we can be able to plot. Then val accuracy, history, then epoch age and everything. Then we plot fig size. Here's a plot, so it's going to plot to separate graphs here, not graph, this one Canva, the 2 subplots here. And then yeah, we can visualize. So this is the training loss, This is the validation. The curve is not that smooth. That means we have some instances like here. Is overfitting. Here is underfitting. So this is just a base model. We're going to see how we can improve it. So that's it about our model. Then we prepare test DF. All the processes that we have performed to DF train above, we do the same to our DF tests to make it consistent and zipping, loading the CSV files and everything. The data gen. Then here we predict. So we have prediction is the model. Test gen. Test gen is now the pre-processed DF tests. And our boss, we can see live as it making the predictions. And then here I prepare my submission file. I define the class, and then construct data frame with IDs and prediction probabilities, and then save to CSV file and then submit. When I submitted this one, the first I submitted, I got a public score of 5.4116. And the first one, maybe we can see the leading has a score of 0.5. So you can see it's a huge discrepancy. We need to do something to improve our model. So I'll try transfer learning to see whether we can up our public score. So see you in that video. And now we are going to make use of pre-trained model to see whether we can improve our model. We are going to make use of mobile net v2. It's a lightweight CNN model optimized for mobile and edge devices. It was developed by Google, having been trained on ImageNet datasets of 14 million images. And, the first thing we need is to load our mobile net v2 pre-trained model. We can see we have loaded it, and we need to include top. This one include top force. It removes the original classification head, and the input shape here ensure that the images are resized to match mobile v2 net input. And then we freeze all the layers. We don't freeze. The freeze here is false, so that the weights don't change during training. This one allows the model to retain its knowledge from ImageNet. Then we add our customed image. We have the base model. This is the model that we have defined here, or we have initiated here. And then we add a few global average pooling. This was max pooling, but now here we are going to make use of average pooling. Then we have the dense layer of 128. Then we use activation, then dropout to prevent overfitting. And then we have output layer. Here we have train generator.class indices. Activation here is softmax to turn the output into the prediction. And then we compile the model here and print. We are going to make use of Adam categorical cross entropy. We have already seen that, and accuracy. And this is the summary of our model. It has so many layers. You can see here so many layers. You can scroll. You can see how big is compared to our base model. Yeah, we have so many layers. And you can see the first model didn't have non-trainable params, but now here in our case we have non-trainable params. And you can see this one, the first model where we performed our base model, it had like 23 million trainable params, but here now you see there are very few, 2 million. Yeah, then from there we need to now perform a few things. We save our model. This is the directory to save our models. Then we need to do a few things here. Call back to save the model with the best validation accuracy. As we train the model, if the model does not improve, we are not going to save it, but save the model that is the best. So that's the file name, that's the monitor we have there to monitor the val accuracy. Then just save the best, don't save the weights. And here we have the mode, here is max to maximize validation accuracy. Then here we have the history, train generator. In this case we are not in this case we have the train generator, we have already done that there. And epochs, then we have validation data, and then we have the steps here, the batch size, the callbacks to check the history and include model checkpoints. So I trained the model here for that epochs. Trained took quite some time before it finished, took almost 2 hours. Yeah, finished. The accuracy, the maximum accuracy here was 62, and var accuracy here was 62, var loss here 1.0. And then we need to view our curves. So compare this one to the model, the base model. You can see this one is performing quite well. Both the training accuracy and validation accuracy, they are improving, they are going up, and the training validation errors here, they are going down. So it's good, and I don't detect any kind of overfitting. If it is there, it's very minimum. Then I prepare my testing data. If you already seen these, and do the prediction. And when I did prediction, so after I did the submission, I got 2.0. Remember the first one got 5, so it has improved by 3 steps, and the rank has improved. So if I wish to improve my model, I can try another type of transfer learning, use another pre-trained model, and see how we can do. So that's all in this video. Thanks for watching.